This is example 5-4. We have water flowing through a little fountain here, right? Comes up on the top, goes in this first bucket, first little cup, I guess you could say, and then drains out at the bottom of this one and flows into the second one, and then continues on down. And we are now asked to figure out what the value for H would have to be for the flow to be steady. So we can start out by saying, well, the flow is steady, and then we'll figure out what H is. And we'll start with cup A, right? So we'll figure out all we need to know from cup A, because we're given the height there, and then based on that we can figure out what happens in cup B. And so to do that, we'll start with a Bernoulli's equation. We're going to go maybe in red so we can see this better, right? We'll assume that we have a point right here. We'll call that point AS for cup A and surface, and then we're going to go down to point C right here. So let's get that started. We can say for cup A, what do we know? We know that both the water surface and point C are going to be in contact with atmosphere. So we can say AS and C both in contact with atmosphere. What does that mean? That means, of course, that the pressures there are equal to atmospheric pressure, which means gauge pressure is equal to 0. So we'd have PAS equal to PC is equal to 0. That's nice. That's two terms that we don't have to worry about anymore. Then let's think about, we said this is going to be steady flow, right? So that means that the water level in this cup doesn't change, right? It says it's 100 millimeters, so it's not going up and down. What does that mean? That means if I think about my streamline going downward here, right? If this was my streamline, right, then I know the velocity that's going downward here at the water surface is going to be equal to 0 because the water level doesn't change, right? So water level is constant, which means that VAS equal to 0. Okay, another term that we dropped off. Right? So we are out of the 3 of the 6 terms. And then lastly, we have to set ourselves a datum. We'll set ourselves a datum at the bottom of the cup. Datum at point C. What does that mean? That means that my ZAS is going to be, if I count from there, right, that's just going to be 0.1 meters, and ZC is equal to 0. Another term that we lost, right? So now let's write our Bernoulli's equation, and then we can strike off all the stuff that we don't need. So we said we have PAS over gamma plus VAS squared over 2G plus ZAS is going to be PC over gamma plus VC squared over 2G plus ZC. Now let's see, what do we have? We said ZC is equal to 0. We said PC is equal to 0. We said we know what ZS is. We know, and we say what PAS is equal to 0. And then we also said that VAS was equal to 0. So all we're left is with VC and ZAS. And ZAS we know, so we can solve for VC. So we can say that VC squared over 2G is equal to ZAS, and of course we can solve that for VC. So let's do VC squared would be 2 times G times ZAS or VC is equal to square root of that. All right, that seems to make sense, right? I mean, depending on how full this cup is, it's going to impact what the velocity is here, right? The more water sitting on top of there, the more it's going to be pushing out. All right, so we have our VC, but that doesn't really tell us what this H is, right? So we have to also look at cup B. And to do that, let's draw ourselves a little bit of a control volume here. Right, we'll need to think about this. So we have, if we just take the water as the control volume, then we'd have this. Now, if we say this is a fixed control volume, right, because we want H to be constant, then what are our inflows? Well, we have our inflow, or our control surface, right? We have a flow coming in here and a flow going out there, right? So we'd have an A here and an A there. And the V is coming downward, so we'd have a V there, and it's still going down there. Okay. So based on that, we can now write our continuity equation. Right? Again, let's say for cup B, for cup B, what do we have? We have fixed control volume. We have steady flow, right? Because we want to have that level to be constant. We have incompressible fluid. Incompressible fluid, and we'll use average velocities. All right, so fixed control volume and incompressible flow, right? It means that we don't have any changes in here, so we can get rid of the dV rho dt term. So that's just going to be 0. And then we just have inflows and outflows. If we look at the top here, we have the water flowing downward, but the area pointing upward, so that'll be negative. So we'd have negative VC times AC. And then at the bottom, we have in the same direction. So it'll be VD times AD. Now, one thing that, of course, we kind of have to assume here is that we'll assume that the size, the diameter of this flow as it's coming down is not going to change. Right? We're going to say it stays at 20 millimeters. And all this is equal to 0. So we can now go ahead and try and get VD from this. Right, that would be the only unknown in this case. So we could say that would be equal to VC times AC is just pi over 4 times DC squared. And then that's equal to VD times pi over 4 D squared. Now, of course, that means our pi over 4's cancel out. And then we can say, if we solve this for VD, well, we can plug in our VC. So VD would then be DD squared over DC squared. Have that right? We're looking for VD. Looks about right. Getting this correct. V. If I have, oh no, the other way around. Getting myself confused here. Why do it be? If I'm getting VD, then I have to divide by that. So DC over DD, and of course times VC. All right, so DC times VC divide. Okay, that makes sense. So that would be DC squared over DD squared, and then we figured out that VC was this up here. 2 times G times ZAC. All right. So what can we do then? Well, we still don't have the height, right? But we can say we can take a little piece of water here, and we can move it to there. Single streamline. So we can do Bernoulli's, right? So we can say, just like before, it's the same streamline, it's still an ideal fluid and steady flow. So we can say in our case PBS over gamma. Probably should define where BS is, right? We just put a dot there, but let's say this is BS. Right, so you can say PBS plus what do we have? We'd have VBS squared over 2G plus ZBS equal to PD over gamma plus VD squared over 2G plus ZD. All right. So what can we gather from there? Let's see. All right, we're still looking for H to come into the picture. So let's look at our pressures first. What are our pressures? Well, I know that both BS and D are in contact with atmosphere. What does that mean? That means, of course, that PBS is equal to PD is equal to 0, just like we had before. Just like we had on the other cup, right? The water level in this cup doesn't change, so that's VBS is going to be 0. It's a little tricky to think about this, right? Maybe we should think about VBS being somewhere over here, and this being the streamline, right? That makes it a little easier to think about it. So we can say water level in cup B is constant. That means that VBS is equal to 0. And then we have to set our datum somewhere, right? We'll set the datum at the bottom of the cup. And that's finally we got our H into this whole thing. So we can say datum at point D. So that means, of course, that my ZD is equal to 0 and my ZBS is then going to be equal to H. Right? If we look up here, this is our datum, then the height there is just H. So we finally got our H in here somewhere. All right, so if we have all that, then we can look back into here, right, into our Bernoulli's equation. We said PBS is equal to 0 and PD are equal to 0. We said ZD is equal to 0, and we said VBS is equal to 0. So just like before, which makes sense, it's the same setup. We just have VD and ZBS, and of course ZBS, put that in here, is just H. Right, so if we write that down here, then we'd have H is equal to VD squared over 2G. And then we can go back up here somewhere where do we have our VD right there. Right, so that then means put a square bracket around it. So that would be DC squared over D squared times 2 times G times ZAC. All of that squared, because it was VD squared, divided by 2G. All right, let's see. So that's then, we pull that out in front here. So that would be DC to the 4th divided by D to the 4th times, and now this square root, of course, gets canceled out. So 2 times G times ZAC, right? Square root to the 2nd power divided by 2G. So if we combine those two, just do the ratio and then square it, dd to the fourth, and then what's left, that 2g cancels out, so just ZAC. All right, so if we plug that in, let's see what our DC was 20 millimeters and DD was 25 millimeters. So that would be 20 millimeters is 0.02 meters divided by 0.025 meters to the fourth power, and ZAC, that's not a C, that's an S. Good that I can't write my own, read my own handwriting. That was 100 millimeters. So times 0.1 meters. So it should be an S here, of course. S, where else? Up in here. S, all right. And if we plug that in, we get 0.04096 meters, or 41.0 millimeters. All right, so that would be, if we wanted flow to be steady, then we'd have to have 40 millimeters in here. So unlike what this picture looks like, where it looks bigger, like the depth here actually would have to be about has less than half of that. All right, so this is how we set it up. And it makes sense that it only depends on the diameters of these outflows and of the height of the other cup, right? That all seems to make sense to me.